What we can notice is that the width of these confidence intervals is smaller when I'm making predictions for a value of x that's very close to the mean of all the x's, and these confidence intervals for the mean of y are wider when I'm making predictions for values of x that are farther from the mean of the x's. And that comes from this particular term that was part of the equation for the standard error when we were calculating the confidence interval, right? And this is a side comment. When I'm saying, the word I'm saying here is not, x not, okay? As opposed to not. I'm not saying not, I'm saying not, okay? Now, of course, I could calculate this kind of confidence interval for the mean of y for any particular value of x, and so I can connect the dots. You get this shape here showing you that these confidence bands, which are meant to tell you where the line seems to go, where the mean of y given x is, are narrower when we're near the middle of the x's, because that's where we're more sure about where the line is. And these confidence bands are wider when we get away from the mean of all the x's, because that is where we're less sure what the mean of y should be. But now we're going to move on to a different idea. This is not what a prediction interval is. This is what a confidence interval is. But now suppose that I have someone new enter the room, okay? Here is her value of x naught. And I am not interested in what the mean y value is for people with her x naught, but rather I want to know the whole range of possible values. For example, suppose that x is height and y is weight. Someone enters the room, she has a certain height, and what I want to know is the whole range of weights that she might have, right? Like, I don't know, maybe I'm supposed to give her a t-shirt to wear, right? So if I know how tall she is, what's the range of weights that are appropriate for someone of that height? Or maybe we're trying to predict college GPA with high school GPA. If this value of x naught is her high school GPA, I don't want to know the mean college GPA for someone who has her high school GPA, but rather I want to know the entire range of college GPAs that we see for people who have her high school GPA. So here's the way to think about it. We have this line, but of course we know that the data, these are the actual data points, the data points vary around the line, right? That's what the linear regression model says, that the points are equal to the line plus some random noise. And so what I'm trying to do now is not make a confidence interval for the mean of y given x, but rather make a prediction interval that covers the entire range, or 95% of the range of values of y that we'd see for a particular value of x. So how will I calculate this? Well, the mean is the same. In other words, the middle of my prediction interval is the same as the middle of my confidence interval. If someone walks in the door and has a particular value of x naught, my best guess at y is still beta naught hat plus beta 1 hat times x naught, right? That's still my best guess. So let's label that here. So we can get to that. Right, here's x naught, and then, all right, there's intercept plus slope times x naught. That's my best guess. But now I want to add or subtract 2 times the square root of some kind of variance. And it's going to be the variance of the actual data points around that mean prediction. Not the amount that I think the line might vary, but the amount that I think the actual data points might vary. Not where the mean of y lies, but where the actual values of y lie. Now, there's actually 2 sources of uncertainty here. There's 2 reasons that I don't know exactly what a particular person's y value will be. One of the reasons is that I don't know exactly where the line is. That's what we've already talked about. I had a confidence interval for the line, so I'm not exactly sure where the line should go. I have uncertainty about that. And then in addition to my uncertainty about the line, I know that there's going to be a residual, that the point itself will be above or below that line. So the first thing I'm going to do is just copy down the variance that we use for the confidence interval, sigma hat squared times the quantity 1 over n plus x naught minus x bar squared divided by the sum of the square distances on x, okay? And these things, this whole part, reflects my uncertainty about where the line goes. It's my uncertainty about the mean of y, given that x is equal to this particular value of x naught. So I'm not done yet, right? So if I stopped here, this would look exactly like the confidence interval. What I'm saying is, one of the reasons I'm not exactly sure what a particular person's y value is that I'm not exactly sure what the mean of y should be for any particular person. But in addition to that, here's the new part. In addition to that, I know that the actual y values vary above and below the line. How much? Well, the residual variance is sigma hat squared. So this extra piece that I've added is the estimated variance of the residuals. My prediction interval for a particular value of x, in other words, x naught, is going to consist of my best guess, so beta naught hat plus beta 1 hat times x naught, plus or minus 2 times the square root of the variance that incorporates all of my uncertainty about where y should lie. Part of that uncertainty is exactly where the mean of y is. And then in addition to not knowing where the mean of y is, I have uncertainty about how far above or below the actual y data point will be. And so you can see that this extra term that I've added here, this one, is going to make my interval much wider. Because now what I'm going to have, in terms of prediction intervals, are these bands that are still, let me label these as prediction bands I've drawn now. These prediction bands are still a little narrower near X bar and a little wider elsewhere, and that's because I still have this part here where I'm taking into account how far X naught is from X bar, but that amount is now minor relative to this very big value here, which is reflecting the amount that the actual y values vary from x. In other words, the residual variance itself is now overwhelming my uncertainty about the line. In general, this quantity I've circled in green, the sigma hat squared, is going to be bigger than the sigma hat squared times this tiny fraction. My uncertainty about how far the point is above or below the line is usually greater than my uncertainty about exactly where the line should go. And so for that reason, my prediction bands tend to be much wider than my confidence bands. And in fact, you often can't even tell that the prediction bands are curved because it looks pretty much like it's just the line plus or minus sigma hat, since sigma hat squared overwhelms the other term that ends up in here.